Good. Okay, so this is the section for February 20th. We're going to start by going over the answers to the homework. The answer key is on Courseworks now. So the first question was about the elliptical distribution for a given Cholesky factor of the conditional covariance matrix. A lot of times, if we want to use this distribution as a likelihood for data, we would have to estimate the conditional covariance matrix, or equivalently, its Cholesky factor. But in this case, we're just generating data from the distribution, and we can take L as given. So we just set that up in R, and we want 100,000 simulations, so we indicate that. And then the rest of it is just creating a spherical variable and then transforming, first a variable on the surface of a hypersphere, or in this case, just a sphere because it only has 3 dimensions, scaling that variable on the surface of a sphere by a random radius to obtain a spherical variable, and then transforming a spherical variable by pre-multiplying it by L to obtain an elliptical variable. So this involves some techniques that we had on the slides, one of which the slide on the elliptical distribution that we didn't get to, but it's fairly straightforward given what we did get to. So we can create a matrix of Z's, which is just going to have independent random normal draws in it. Then we can use the sweep function to divide each column. So Z is going to be a matrix with 3 rows and 100,000 columns. Then we can use the sweep function to divide each of the 100,000 columns by the square root of the sum of squares within that column. So this will create a 3 by 100,000 matrix U, where each of the columns is a random draw from the surface of a sphere. And then we can multiply that by L to have something to work with intermediately. Then different groups had different distributions for the squared radius. In general, any positive distribution on a positive sample space would be a candidate for the squared radius. So some groups had a beta distribution with parameters equal to 1/2. So you just draw from a beta distribution with those parameters. That gives you R squared. Take the square root of that. That gives you R. Similarly, other distributions, absolute value of a standard Cauchy, chi-squared distribution, 1 degree of freedom, standard log normal distribution. It's all basically the same process. Draw from the appropriate distribution to get a realization of R squared. Take the square root of that. Now you have 100,000 R variables. Again, we can use the sweep function to multiply each column of LU by the realization of R using multiplication. And then we can plot that in 3 dimensions to get something that looks like this in the case where R squared comes from a log normal distribution, but you should get something similar, maybe with different scales on the axes, depending on what distribution you had. But in any event, it looks like an ellipse. In 2 dimensions, it would look, if you look at any plane, it would look even more like an ellipse, and that's why it's called an elliptical distribution. Any questions about that one? Nope. Moving on. Question 2 was an analytical one where you have a likelihood. This happens to be a distribution called the Gompertz distribution, or a standard version of it. There's another parameter in general, but I've set that equal to 1 on this problem. And then we had a gamma prior, although in this case the gamma prior is parameterized in terms of an inverse scale parameter beta. I think previously we'd done the gamma parameterized in terms of a scale rather than an inverse scale. But you'll see it both ways, and the one with inverse scale is actually used by Bayesians more because there's a variety of distributions that are conjugate with the gamma. Particularly, it's easiest to derive using an inverse scale parameterization rather than a scale parameterization. And then looks like it ate the output. Okay, so if you're on YouTube, look on the answer key that's on Courseworks. So with only one observation, you have a prior in red, a likelihood in blue. Substitute in the particular forms for that. In this case, we know that beta to the alpha is going to be a constant. It doesn't depend on lambda. Same thing with gamma to the, evaluated at alpha. That doesn't depend on lambda. And e to the y is also not going to depend on anything relating to lambda. So if we just get rid of those constants, write it in terms of proportionality again, we get some terms involving lambda raised to powers, some terms involving e raised to powers, utilize the result that the product of the same base raised to different powers results in the same base with the sum of the new power. In any event, we can factor this around until we get something that has the same kernel as the prior distribution. In this case, it would be lambda to the alpha star minus 1 multiplied by e to the negative lambda times beta star, where alpha star is equal to the original alpha plus 1, and beta star is equal to the original beta plus e to the y minus 1. And we can see that that kernel has the same kernel as the gamma prior that we had before. So the posterior distribution is going to be a gamma with updated parameters. Similarly, if we have n independent observations, now our likelihood is a product over a bunch of Gompertz distributions. We proceed in the same way, and we get a result alpha star is equal to n times the original alpha, and beta star is equal to beta minus n plus the sum of squared e, or sum, not squared, just sum of e to the yi's. So what we had before was a special case where n is equal to 1. And if you think about it, you could see, this that we have here would be the result of applying what we got on the previous part of the problem n times. So if we got one observation, we could update the prior distribution to the posterior distribution. It's now going to be a new gamma. If we got a second data point, we would update that gamma to a new gamma. If we got all the way to the nth data point, we would be updating a gamma to a new gamma. And the gamma that we would end up with is the same as if we got the data all at once and applied this second result here. So this illustrates the principle of Bayesian updating in the most straightforward form, that it doesn't matter for exchangeable data points. It doesn't matter what order they come in or how many groups that they come in, anything like that. You end up with the same beliefs at the end. So questions on number 2. Question 3. So this one involves logarithms and e, the number e. So that can be numerically unstable, as we talked about last week. So the biggest number that a computer, a typical laptop computer can raise e to the power of is a little bit less than 710. Anything bigger than that, and R is just going to say that's infinity. So anytime you might have numbers that big, you can run into problems with using E, because if anything does what's known as overflowing and R just counts it as infinity, then infinity minus something is still going to be infinity. It's just going to stay infinity until the end of the calculation, and most likely result in a error message. So that's why one of the reasons why we usually, when doing Bayesian numerical stuff, are working with the log of the posterior distribution. So as long as we don't have to actually raise anything, e to the power of 1,000 or anything like that, it's still going to remain within the numbers the computer can easily handle. On the other side, anything that's less than about 745, e to that power is going to evaluate to 0 as far as R is concerned. And that's what's known as underflowing. Underflowing is generally not as bad a problem as overflowing, because if something shouldn't be exactly 0, but the computer thinks it's 0, then you're sort of off by something in the 16th decimal place, but the calculation can continue, and most likely you're not going to care about any accuracy beyond like the 2nd decimal place anyway. But overflowing basically means it's never going to get away from infinity numerically. So one form of a log likelihood could be written this way: a log likelihood function for a binomial or Bernoulli distribution summed over n observations, where you have one coefficient beta that enters the likelihood with a logistic link function. And so as we talked about last time, it's good to use the function log 1p when having to calculate logarithms involving a construction 1 plus something. And for the logistic link function, that can be defined as 1 divided by 1 plus e to the negative x beta. And so that has a construction that's consistent with the log 1p thing. Although we didn't talk about it last Friday and you didn't need to do it on the homework, there's an even better method that is used a lot in Stan and other good programs that utilizes the fact that log of the quantity e to the a plus e to the b can be expressed as m plus log e to the a minus m plus e to the b minus m, that quantity, where m is the maximum of a and b. And so basically it does a numerical pivoting strategy. So either a minus m or b minus m is going to be 0, and e to the 0 is 1. So there's no numerical error there. And also, because you have a 1, then you can use the log 1p function again, which is going to be more numerically accurate for small values that are added onto it. But the main thing on this pivoting strategy is to minimize the chance of overflowing. So whatever is the biggest one, the smaller one, you subtract the bigger one from it, and then you don't have to worry about overflow on the other term. You just maybe have to worry about underflow, which is not as bad a problem. So there's a function, it's called log sum exp in Stan, and I wrote it out here, although I didn't actually use that function. I used the one previous to it to do the log likelihood. And you could check that your answer is correct because the Bernoulli distribution doesn't have any constants in it. You could just evaluate the sum of log Bernoulli densities. So that happens when you put size equal to 1 into the binomial distribution and evaluate it at the probability of x times beta transformed with the standard logistic CDF. So you should get the same answer for the likelihood. And we can plot the likelihood it looks like this. Has a maximum likelihood estimate close to 0, which makes sense because y, the way it's constructed, doesn't depend on x at all. We good? So that's what the likelihood function is. And then the kernel of the posterior distribution can be written as the sum of the log likelihood and the kernel of the prior in logarithm form. It's important to remember that although you're summing over n observations in the log likelihood and dropping the constants if there were any, the prior only enters the posterior once. So it's the sum of those terms. If we had a hierarchical prior distribution, then it would be the sum of many layers in the hierarchy. But the prior as a whole is only going to enter once, whereas each data point enters the likelihood once, and you sum over that. Again, different people had different prior distributions. Later on in the question, it said you could choose any hyperparameters you want, provided that the standard deviation of the prior was equal to 1. So you needed to look up what is the expression for the variance of that distribution, and then choose the hyperparameters accordingly. And then when you write the log prior kernel, you just need to not include any constants in that, things that don't depend on beta. Now, in truth, the constants, if you had them, they wouldn't hurt anything. And so, it would make more sense to just use the functions in R that have the distributions with the constants included in them. But those distributions are already there and they've been tested and everything like that. So you might as well have just used them. But in general, if you're writing your own distributions and stuff in Stan, it's just going to take additional time and flops and whatever to recalculate constants all the time that are not going to have any bearing on the posterior distribution or the likelihood. Yes, sir.
So I think I'm actually just making you repeat yourself, so I apologize in advance. But just to be clear, if we had not bothered to drop any terms not depending on beta, it wouldn't have really changed much substantively. It would have just made it harder for the computer to calculate the kernel. Is that? Yeah,
it wouldn't have changed anything substantively. It would have changed the units on the y-axis, right. But for a frequentist, they're only interested in the mode, so the units on the y-axis don't really matter.
Yeah.
And a small amount of time lost would be, calculating the logarithm of 2 over and over again, or whatever. So it was really just a practice exercise in figuring out what the logarithm of one of these prior distributions would be. And then depending on what log prior you have, then you can use the inverse CDF method that's implemented by the R Uniron package. You just want to use PMNu to get an approximation of the inverse CDF that corresponds to your kernel function. In this case, there's no lower bound or upper bound on beta. It's a real number. So you can just specify those as infinity. Center, you could just choose any reasonable values, such as the mode or the mean of your prior distribution, to help out its approximation there. And then pass that to the UR function to generate a whole bunch of draws from this posterior distribution, which doesn't have a name except for the posterior distribution of a univariate logistic model with whatever prior you happen to have here. So if we look at a histogram of the posterior distribution of beta, we could see, in this case, it was the mean of it was the median of it was slightly greater than 0, but there's certainly a lot of posterior density on both sides of 0. We didn't have that many observations here, but clearly the data generating process had a true coefficient of 0. So our posterior distribution is not inconsistent with that. All right. Question 4 involved MCMC pack. Again, you needed to make n be 10 in order for this to work in practice, but it would work in principle even with smaller n, provided you had proper priors. So you just draw x, construct y with this form here using normally distributed errors. Then you can draw from the posterior distribution using the MCMC regress function, which is basically just as easy to use as LM, except you can if you want. And in this problem, the question required you to want to specify proper prior distributions. By default, it uses essentially improper priors on the parameters, which for a regular just toy regression problem is usually going to be fine. I put in some values here that might have been approximately reasonable, but any proper priors would be adequate for this question. And then the harder part of this was to draw from the posterior predictive distribution. And I think the posterior predictive distribution is something that a lot of people have not really wrapped their heads around yet. It's just your posterior beliefs about the outcome, or if you want to be more specific, about a future outcome generated from this data generating process. And your beliefs about a future outcome depend on your beliefs about the coefficients and about the error variance. So to draw from a posterior predictive distribution, it's a lot easier to do than perhaps it is to understand, but it isn't difficult to understand. And hopefully, if we get a little bit of practice with it, then it will be something that everybody is comfortable with. So in this case, the problem said we want the posterior predictive distribution given x, where x is a vector that is constructed from the sample medians. So this is kind of a typical x maybe. And then the next line here, we want to draw y tilde, the same number of draws as we had in our posterior distribution. It could be more, it could be, or it's easier to make it exactly the same. It could be less, but you already have the draws, so you might as well use them. And then the expectation of that univariate normal distribution is just going to be x times beta. So we have a matrix of posterior draws that's like 10,000 rows and 11 columns or something like that. And so in order to get a vector of length 10,000, we're just going to post multiply that by the x median vector. And then for the standard deviation to this univariate normal distribution, we're just going to use the square root of the draws of the posterior error variance. And so now y tilde is a vector of length 100,000 or 10,000. And we can make a histogram of that distribution to say what are our beliefs about what a future y would be in light of our updated beliefs about what the betas and what the sigma squared is. And if that, each observation in y tilde, each element of y tilde comes from a conditional normal distribution. But the overall distribution of y tilde for all 10,000 elements is basically marginalizing over the distribution of beta and the distribution of sigma squared. And so we get a posterior predictive distribution of y that has more dispersion than a normal distribution. It's similar to the thing that we did with the Poisson gamma. It's similar to the thing that we did with the second roll for how many pins you knock down on bowling. You have to marginalize out the stuff that you don't want. or for this purpose, the stuff that you don't want, in order to get a marginal distribution of the thing that you do want, which in this case is y, and y that does not condition on the unknown parameters, because you've marginalized over the parameters, leaving a marginal distribution of y that only depends on the data that you observed previously and whatever values you use for the hyperparameters. So each one of these y tildes is conditionally normal, collectively marginalizing over the parameters. They have some unnamed distribution that by construction is going to have at least a little bit more variance than a normal distribution would. Jasper, you had a question?
Yeah. When you take the median, there you're getting the median of your intercept, right? So
yeah, that's just one.
Yeah.
Anyway.
Yeah.
So I put a normal curve that had the sample standard deviation of y tilde and the sample mean of y tilde as its parameters, and you can see the histogram is poking outside of that, reflecting the fact that any marginalized distribution is going to have more variance to it, if the variance even exists, than the conditional distribution that it marginalized over. Okay. So that was it for the problems. Any more questions about those? No? All right. So there's a file on Courseworks that you can download and unzip. I'm just going to switch my panes. All right. So today we're going to use the chunk norm package in addition to some stuff that you've probably already downloaded and used. So the first topic I want to consider a little bit more about the limitations of a Gibbs sampler before we get into actually using some Gibbs samplers. So in order for a Gibbs sampler to work, someone, perhaps you, but more likely someone already, has to derive what the full conditional distributions are for each of the parameters. Again, full conditional distribution is the conditional distribution of theta k, conditional on all the thetas except for theta k, where theta is just a big vector of all the unknowns in your posterior distribution. And then once you actually, writing the kernel for the full conditional distributions is never particularly hard. You just drop a whole lot of things that are constant, and left with a kernel that only depends on functions of theta k. However, you have to be extraordinarily lucky, or more likely extraordinarily clever in your choice of likelihood and prior distributions, in order for all those full conditional distributions to be named well-known distributions. And if it's a named distribution, there's a good chance that there's a function in R, or maybe some R package, or somewhere on the internet that would describe an algorithm for drawing from that distribution. And if you're able to draw from each of the full conditional distributions, at that point, a Gibbs sampler is pretty easy to program. And we'll do one later in the section. But if you don't have named full conditional distributions, at least some of the full conditional distributions are not named, then you're going to have to do something else. So you do have a perfectly valid posterior distribution. It's just you have a posterior distribution that does not lend itself to Gibbs sampling the same way that a posterior distribution that factors into named full conditional distributions would. And for that reason, most of the Gibbs samplers, which have been used a lot for Bayesian analysis the past 20 years, are a little bit artificial in the sense that people derived what the full conditional distributions are for basically clever choices of priors and likelihoods. They chose those priors and likelihoods in order to get named full conditional distributions, which are generally going to involve conjugacy. So the full conditional distribution is going to be of the same family as the prior distribution, just with different values of hyperparameters in light of the data that comes through with the likelihood. And that's a little bit unsatisfactory, and we'll start addressing that next week. So if the Gibbs samplers are essentially limited to situations in which you have conjugate relationships among variables, what are the distributions that have that property? And it can be shown that for any distribution that's in the so-called exponential family of distributions, which includes the exponential distribution and a bunch more, there is a conjugate distribution. And so what's the exponential family? If you compile this, it's probably a little bit easier to read. But a distribution within the exponential family is one that can be written as a function of the data times e to the power of the dot product between eta and t, where eta is what's known as the natural parameters, and t is a vector of sufficient statistics that depend on the data. So a sufficient statistic is a function such that conditional on that sufficient statistic, the data and the parameters are conditionally independent of each other. There's also another term in the exponent of the e, this a business, but that only ensures that the exponential, the distribution that you're talking about from the exponential family integrates to 1. So it's a function of the parameters only, not the data and the likelihood. So those are explained there. The most important property, or the most interesting thing about these exponential families, is this sufficient statistic. So something that you can calculate a scalar, sometimes two scalar functions that basically contain all the information in the sample. And thus, in order to obtain the maximum likelihood estimates, you just have to, so binomial is an example of exponential family. In order to obtain the maximum likelihood estimates, where's my maximum likelihood estimate thing? Yes, you take the logarithm of the thing, and so the h business is going to be a constant. The logarithm cancels out the e, and so you're left with natural parameters multiplied by sufficient statistics minus this constant thing. That's your log likelihood. You take the derivative of that with respect to the parameters, and you get a relatively easy first order condition. It might have an analytical solution. Oftentimes it does, but if not, it'll have a numerical solution. So it's a pretty easy way to get maximum likelihood estimates. And thus, but the other, I think I said this already, but just to reemphasize it, if the likelihood is within the exponential family, then there are prior distributions that are going to be conjugate with that, in which case you might have an analytical posterior, or you might be able to get analytical full conditional distributions, so to sample from a Gibbs sampler. But another important point is that these distributions in the exponential family are the ones that you're most likely to have heard of, and they're also the ones that are most amenable to calculating a maximum likelihood estimator. And so they're used, or perhaps overused, by frequentists a lot. In addition to having sort of a relatively easy computational algorithm for obtaining maximum likelihood estimates, if the likelihood is from the exponential family, it also tends to imply that the maximum likelihood estimator is going to be pretty good, even if you have a smallish sample, even though maximum likelihood estimates, we can only guarantee their properties as the sample size goes to infinity, again, holding the number of parameters to estimate constant. And you can sort of understand that in a very intuitive sense if you always remember maximum likelihood estimates don't condition on the data. They are the parameter values that maximize the probability of you observing the particular sample that you have. So it does the conditionality the opposite way of the way that would make sense, which is the Bayesian way. And so given that a maximum likelihood estimator in general does not condition on the data, you might say that it's inefficient. You can't say that it's inefficient because inefficient is something that means something very particular to frequentist. But by inefficient, I mean if it's not conditioning on the data, it's not really using all the information that you have in the sample to obtain estimates. But the exception to that is situations where the likelihood comes from the exponential family, in which case the sufficient statistics basically concentrate all the information that there is in the data into these t functions that get multiplied by the parameters. And hence, in that situation, the maximum likelihood estimators are not inefficient. And as the book, it has a link to this on the syllabus, Jane's book that was published after he died, he sort of, summarized this, saying, basically maximum likelihood estimation was developed by Fisher in the 1930s, or in fact earlier, and hasn't changed theoretically since then. We have computers now that makes it easier to get maximum likelihood estimates numerically, but that doesn't really change anything fundamentally from the way maximum likelihood estimation was when Fisher basically invented it. And the problems of the 1930s are very different from the problems that researchers are interested in today. But the problems of the 1930s tended to have a fixed number of parameters that was not so big. Likelihoods that were chosen from the exponential family, so they had sufficient statistics. No prior information of real use, and basically all the parameters were of interest. The problems that we tend to have, researchers are interested in today, are more things where we might be estimating one parameter per person. So there's a lot of them. The number of parameters to estimate goes to infinity as the number of people goes to infinity. But we might have some important prior information that the way in which the data generating process differs from person to person is something that is a difference of degree rather than a difference of kind. So we'll talk about that when we get into hierarchical modeling. We're not certainly limited to distributions that come from the exponential family anymore. So if those conditions are met, then maximum likelihood estimate tends to be, the sampling distribution tends to be a good approximation to the posterior distribution. But when those conditions are not met, then maximum likelihood estimation can certainly be not good in small samples. And it doesn't have as much of a philosophical justification because it's not conditioning on the data. It's not using all the information that you have in the data. And that really bothers Janes, that he was criticized as being subjective by frequentists who thought of themselves as being objective, but the objective frequentists are not even using all the information that they have in the data if the likelihood is not one of these that has sufficient statistics in it. So unfortunately, in a manner of speaking, maximum likelihood estimation, it's still, you can do it even if you're using a likelihood that's not from the exponential family, and a computer might not end up in an error message. And so as we've gotten computers like 30 years after Fisher, people are pushing maximum likelihood, beyond the situations in which it was originally developed and is known to work reasonably well, to likelihoods that are not from the exponential family, or you've got lots of parameters. And because the computer doesn't necessarily bomb an error message and you get estimates, people are like, well, maximum likelihood is good because it works in these limited situations, so it's probably going to work in this new situation that I'm trying to push maximum likelihood to do. But there's no reason to really think that sampling distribution is going to be a good approximation of a posterior distribution. And it would be better to take the Bayesian approach. But again, if you're not using likelihoods from the exponential family, you're not going to have the conjugacy that you need to do Gibbs sampling. So we're going to have to learn some other techniques to draw from an arbitrary posterior distribution that doesn't factor into named full conditional distributions. And so I gave a conceptual example of a function here called Gibbs, which uses the R-Uniron black box approach to draw from each conditional distribution in turn. Now, this is going to be extremely slow, and it has a lot of limitations to it. But I just wrote it down so that people can sort of get a conceptual understanding of what Gibbs sampling is. And in principle, a function like this would do for an arbitrary posterior distribution using our Uniron to approximate the inverse CDF. So we take in the arguments, a log kernel of the posterior distribution, initial values that are guessed for the parameters, any lower and upper bounds for those parameters, and how many draws we want to obtain from this posterior distribution. So then we just set up a matrix to hold the draws that we're going to obtain. We iterate for that number of draws, and we iterate over each of the big K parameters. Each time inside the inner loop, we're going to define a full conditional distribution, full conditional probability kernel. So that's going to only depend on the kth, little kth value of theta. And so inside the function, we'll just assign theta sub k to the kth element of theta. That's going to make a local copy of theta that we then pass to the log kernel function that we had to previously define. Then we use what we did on the homework with the PIMD new function to approximate the inverse CDF of that unnamed full conditional distribution. We can use lower bounds or upper bounds if that is appropriate for the kth parameter. And we'll use the existing draw of theta k as our center in order to improve the accuracy of the R-Uniron thing. And then we just take one draw from that, put that into the kth element of theta, and then move on to the next element of theta on the inner loop. Once we get to big K, that constitutes one sweep over all the unknown parameters, and that gives us one draw from the posterior distribution, and we're going to end up with iterations draws at the end, and then we just return our matrix of draws, and in principle, we have draws from any posterior distribution. Now, what bugs and what MCMC Pack more specifically do is rather than taking this black box approach, they're recognizing the situations in which the full conditional distribution is going to have a named, is going to be a named thing, and using a more efficient way to draw from that named distribution than what we have here. In particular, MCMC Pack sometimes is programmed, if possible, that it can make a whole draw from a vector, a subvector of parameters at a time. It'll do that. So if you have like 100 beta coefficients, rather than drawing them just one at a time, it will draw from the whole 100-dimensional distribution of the beta coefficients at once, conditional on the error variance or whatever. And so those specialized algorithms even to some extent bugs, which has relatively advanced pattern recognition capabilities to detect when a full conditional distribution has a kernel that it knows about, are going to be better than this in basically all respects. Stan would be better than this in basically all respects, except for the fact that this one ought to be short enough for you to easily understand what's going on in a Gibbs sampler, with the provision that usually if somebody's going to sit down and program one of these things, they'll do something more efficient to make the draw from the full conditional distribution if possible. Anna had a question?
Yeah, I just wanted to ask what exactly does the second step do, where you assign to full conditional this function of theta k?
Yeah, I feel like it'll switch around.
Yeah, like what can you just say again?
Right.
Exactly?
So in this step, yeah, which is where all the magic happens. So this theta k that it's using for the center is the old value of the kth theta. So whatever theta is now in iteration time. So presumably the next draw of the kth value of theta will be somewhere close to that. And then the UR function takes the result of PIMV new. We did that on the homework. And so what I'm passing to PIMV new is this full conditional function, which I just got through defining.
That's the step that I meant, actually.
Oh,
How you define the full conditional.
right. So the full conditional, the kernel of the full conditional distribution is basically just the kernel of the posterior regarding every parameter except the kth as a constant, taking it as given. So the full conditional distribution could just be a function of an unknown scalar. In general, MCMC-Pack is going to be more clever here and do whole vectors at a time, but this is the sort of brute force approach here. So it's going to, this is the function that our Uniron needs to be approximating the inverse CDF of. And you have to redefine the function each time because the theta besides k are changing every time. So it needs a new approximation. And that's why this is just pathetically slow. But conceptually, it's the right thing to do. And then you just take one draw from that inverse CDF approximation. That's your new theta. And then you move on to our new value of theta k, move on to the next one. And theta k plus 1 is going to be conditioned on what you just drew for theta k and what you most recently drew for everything else.
So this is like that. The full conditional function is just a way of forcing the loop to like basically just vary one of the parameters at a time. Like such.
Yeah. So the full conditional thing is what our Uniron needs to make a polynomial approximation to that function. It needs to know what it is it's approximating. And our Uniron can basically draw reasonably well from any univariate distribution that it knows the kernel of.
Just to be clear on what's going on in Gibbs sampling, so when we take the full conditional distribution with theta k, does it update every single line or does it update every cycle? I don't know if it even matters.
Well, it does matter. So that's why we have two loops. The outside loop is for the number of draws for the theta vector that we want at the end. The inside loop goes through one theta at a time, one element of the theta vector at a time, each time updating it with this R Uniron business.
So theta k plus 1's draw is going to be more right than theta k's draw from this full conditional distribution.
They're ostensibly equally right. A case could be made that the first iteration is less right than the second.
It hasn't been updated by anything.
Yeah. So it depends on where you started out as to how wrong the first one is. So that's an issue that we'll talk about more when we get into Stan and other things. Again, I was just putting this up to, in 20 lines could have a Gibbs sampler. But this emphasizes that not all ways of drawing from a posterior distribution are created equal. Yeah.
As the number of draws reaches infinity, why does it make a difference that we're updating after every draw as opposed to every cycle? It seems like it would eventually, both would eventually lead to the promised land.
Yeah, for a really infinite number of iterations, perhaps. Yeah. Or you wouldn't have to do it. Another thing you'll see sometimes, people not just going on the inside 1, 2, 3, 4K, but going in a random order. Also legitimate. In any event, don't actually use that function, but make sure you understand what it does.
So it's essentially just like treating a multivariate distribution as like a sequence of univariate distributions.
Sequence of univariate full conditional, not sequence of marginals.
Right.
That wouldn't be legit. So what MCMC Pack is doing is basically choosing prior distributions so that the full conditional distributions are known in closed form. If possible, you have vector full conditional distributions so you can get one big piece of theta all at once. And so we're going to use an example from that for a low birth weight model. So the outcome here is whether or not a child has low birth weight, a function of a number of things about the mother, in particular whether she smoked during pregnancy. So in this case, we can use the MCMC probit function to draw from that posterior distribution much faster and in every way better than what would have been done if we'd used the Gibbs function that I wrote. In general, when you get the output of an MCMC pack thing, you just want to do a summary, and it will tell you the relevant, most relevant information about the draws from the posterior distribution. It's actually using another R package called CODA. But in any event, the mean of the posterior distribution on the are you a smoker variable is 0.69. It has a standard deviation of those draws of 0.22. You can see that the 95% interval, central interval for the draws on the smoker variable only includes positive numbers. And so because the probit link function is monotonic, or you have with probability 0.95 or actually greater than probability 0.95 that there's a positive association with pregnant women smoking and the incidence of low birth weight children in these data. So that is pretty straightforward. Don't worry about this naive SE and time series SE stuff yet. We'll get to that in a later week. And in the model like this, those things are so small as to be negligible. So that's what we have. But we would, since the probit model, the Bayesian perspective on it is so simple, it's actually easy enough for us to do a probit model ourselves, provided we have a way to draw from a truncated normal distribution, and the trunk norm package implements that. So we want to get y, which is just a binary variable, whether or not the baby had low birth weight. We want to establish the lower bound and the upper bound. So remember, as we saw yesterday, for the full conditional distribution of y star, it's going to be a truncated normal distribution. And if y is 1, we're going to truncate it from below at 0. So we get positive draws of y star. And if y is 0, we want to truncate the full conditional distribution of y star from above at 0 so that the draws are constrained to be negative. So that's what we do with these two if-else functions. So this says if y is equal to 1, make the lower bound 0. And if y is not equal to 1, which is to say it's 0, then make the lower bound negative infinity. And conversely, for the upper bound, if y is equal to 1, make the upper bound infinity. And if y is equal to 0, make the upper bound 0. So those are the lower bound and upper bound vectors that the R trunk norm function is going to be using to draw from the full conditional distribution of the y stars. So we can use the MLEs in order to make starting values or in order to make other constants that we might need to calculate and use in our Gibbs sampler. So just pipe all that in. It gets X. This model matrix function is very useful. It gets in matrix form the predictors that were specified in your formula for GLM. So in this case, this is going to be 189 by 5 matrix. It has a column for the intercept first, and then the age of the mother at the time the kid was born, 2 race categories, and whether she smoked during pregnancy. And then, you know, other stuff are just functions of X that we can calculate once so that we don't have to keep recalculating that during the Gibbs sampler. And finally, we're going to use the maximum likelihood estimates for beta as our starting values to the Gibbs sampler. So we've got all that. And then we can set up a relatively simple Gibbs sampler. First, we're going to create a matrix to hold all of our draws. And then we're going to loop over those rows. First thing we do is draw from the full conditional distribution of y star using the R trunk norm. So every observation has its utility difference missing. So we're going to take n draws. For some of those people, they're going to have a lower bound of 0. For other of those people, they're going to have an upper bound of 0. So we specified our bounds there. But for everybody, or for each person, the expectation of the, that's not the right way to say it. If it were untruncated, the expectation would be x beta. The truncated mean is actually going to be different from that. In any event, the location parameter for the truncated normal distribution is going to be equal to x beta. That vector is going to be of length n, and we don't have to specify the standard deviation because we fixed the standard deviation to be 1 because the variance of the latent utility difference is basically arbitrary. We could scale it up or scale it down without affecting any of the observed choices that we see. So that would be a draw from the full conditional distribution of y star. Then we need to not rely on the OLS estimates calculated once, but rather we need an updated mean vector. So this is just x transpose x inverse x transpose now multiplied by y star rather than y as we would in the case where we had observed continuous outcome. And then under the assumption which I'm using here of no prior information, the full conditional distribution of the beta vector is equal to that b, which has the form of OLS, but it's random and it's been updated. So that is full conditional multivariate normal distribution for beta, whose mean vector is equal to that b that I just calculated, and whose covariance is equal to x transpose x inverse that I've already taken the Cholesky factor of. And so we can draw from a multivariate normal distribution by taking an appropriate number of independent standard normal draws and pre-multiplying them by the appropriate Cholesky factor. Then we get a draw from beta. We need to keep that being called beta because y star is going to need it the next time around. But we want to hold on to whatever that value of beta is at the ith iteration because we want to analyze the posterior distribution. So if we want to send all that into R, okay, that went reasonably fast, although not as fast as MC and CPAC. And so that is basically the simplest example of a Gibbs sampler that, using closed form full conditional distribution relationships, for that program model. So is everyone comfortable with that? In principle, we could compare it to that thing where I wrote the Gibbs sampler. We're not actually going to do that because it's really slow. But as an exercise, why don't you try to write in that function there, what would be the kernel for this posterior distribution? Anna.
Just so that I understand this, so the fact that we know that it's not very normal in the end allows us to do this last step rather than doing the full conditional distribution for every beta, for every variable that we have in the model.
Right. You can just make it all k of those at once.
Okay.
Or, yeah. So take hopefully like 1 minute to write the, you can assume no prior. So basically this is just a likelihood for your kernel of this probit model, as if you were gonna hand it to the black box Gibbs sampler. through k. So basically the right kernel here, the kernel for the likelihood function of a probit model, is very similar to the kernel of a likelihood function for a logit model, like we saw on the homework, problem 3. It's just the sum of a Bernoulli density evaluated at probability. In this case, we're using the normal CDF as the transformation function rather than the standard logistic CDF as the transformation function, but that just involves changing P logis to P norm. Also, in this case, we have a whole matrix of X variables rather than on the homework, we just had one X variable. We want to use the logarithm of that Bernoulli to be a log kernel, and then we sum all of those for each of the n observations that we have to obtain a likelihood kernel for the whole sample. So in principle, it is very slow, but you could pass that to the Gibbs sampler that I wrote, and it would draw from a distribution that has the same posterior distribution as the one that we did from MCMC Pack, and then the one that we did in R, basically imitating what MCMC Pack does, drawing from truncated normals. So we can compare those two, and we see that MCMC Pack and R implementation resulted in posterior distributions that are very similar, at least at the means. And that's because we're using the same algorithm. So they only differ due to the fact that both have a finite number of draws, and they use different random number seeds for those finite number of draws. But for all intents and purposes, they're the same, which indicates that we did it correctly. Although if you wanted to do it in practice, you might as well just use MCMC Pack's version, MCMC Probit, rather than writing your own. So the last thing we want to do today is, again, go back to this idea of a posterior predictive distribution, which is very important because that's where a lot of the inference happens. So once you've established that the whole drawing from the posterior thing went well, you want to make scientific inferences, and those are usually going to involve functions of the posterior predictive distribution. And so in this case, we might want to know what's the average causal effect of smoking on low birth weight babies. And so to draw from the posterior predictive distribution, again, it's a lot easier than it sounds. You draw from the posterior distribution, which we've already done. And then you use those draws from the posterior distribution as inputs to the function whose PDF is the likelihood. Whatever that function is, you draw from it, and now you have realizations of the posterior predictive distribution of the outcome. And then you can calculate any function of the posterior predictive distribution that you want. So in this case, we're interested in the average causal effect. We want to do as matrix of the MCMC Pack thing to get a matrix version of the results. That's just going to be draws from the intercepts of those 5 variables. Tara?
I had a question. So I was able to run the third column, but the estimates are one different.
That could be because it's not a good function. But in principle, it is right if you were to do like a lot of iterations. It would take at least that long. And it's possible that the R neuron approximations are not very good in the tails. So it's conceptually right, and that's basically all I wanted to convey. So we have a matrix of betas that came from MCMC Pack, so it's the good kind. 10,000 draws from the posterior distribution on each of these 5 coefficients. So if we wanted to draw from the posterior predictive distribution based on the x's that we have, we can use the apply function to each row. And so that's going to give us a vector and we want to draw from a binomial distribution, just one draw per value of x, or this should actually be 10,000. Yes, it should be 10,000. Sorry. From a Bernoulli distribution whose probabilities are the inverse CDF transformation evaluated at this whole x times beta linear predictor. So if we send that into R, we get a y tilde that is, makes sense. So 100,000, 10,000 draws from the posterior predictive distribution for each one of our 189 observations that we have in the sample. We're drawing from its posterior predictive distribution. Then if we want to investigate the counterfactual, so what would it be if you switched smokers into non-smokers and non-smokers into smokers? We just go through and change the last column of X, so it's reverse coded. And we again draw from the posterior predictive. So that's Y counterfactual, and that's going to have the same dimensions as Y tilde. Good. So if we want our model-based estimate of the individual causal effect, we can use the if-else function. So if X, the last column of it, is currently 0, that means the person was originally coded as a smoker. So the individual causal effect for those people is going to be Y tilde minus YCF. And the individual causal effect for the other people is going to be YCF minus Y tilde, although I think my dimensions are going to be off. I want to make this transposed. Now, you can calculate those individual causal effects. We have a distribution of those. A lot of those. Anyway, I think I'm being a little bit loose here, but once you get the individual causal effects, you could average them to come up with your estimate of the average causal effect, which in this case, I think I didn't do it right, but it's something on the order of this number, increase in the probability of a low birth weight baby of 0.37. So that's how you can use the posterior predictive distribution and functions thereof in order to make the ultimate inferences you're interested in terms of functions of observables, but not observed. So future, what you think about the distribution for future data. Okay, so that's all the time that we have today. I put an example of using a multivariate multinomial probit model onto the RMD file that we didn't have time to get to, but the point I wanted to make about that is even though it has full conditional distributions that are named, the Gibbs sampler doesn't work particularly well with it. Neither would the Gibbs sampler that we did with our Uniron. So we're going to need an even more powerful way to draw from posterior distributions than Gibbs samplers in order to handle that multinomial probit model. And that is when we're going to start turning to Stan next week. And right after I get some lunch, I'll put up the readings for next week about that. Okay, the end.